or good afternoon, where you are. On behalf of the IoT4Ag ERC, it's my pleasure to introduce the speaker for the last seminar of the Spring 2023 series. And today we have Professor Chandra Krintz from UC Santa Barbara. She got graduate degrees from UC San Diego and in computer science, and then she joined UC Santa Barbara, where she's currently a professor. And she's also a chief scientist at AppScale Systems. And her research interests are generally in IoT, programming languages, big data, and cloud. And today she will talk about open source on-farm systems for precision agriculture applications. Thanks very much for joining us. We look forward to hearing your presentation.
Thank you so much. I'm thrilled to be here. I have been part of the scientific advisory board for IoT4Ag for a few years now, and I've really been impressed by the group and sort of the multidisciplinary aspects and all of the great work that's coming out of the center. And I'm super excited just to be part of your seminar series. So thank you for inviting me today. I'm going to talk about our work that I think that's going to be most interesting to you. And I just want to mention that this is joint work with the co-lead of my lab, Professor Rich Wolski at UC Santa Barbara. So I work in the Internet of Things, as Stefano mentioned, and it's really exciting time to be in this space. I work on computer systems that underlie the advances that we want to pursue in terms of autonomy and automation and data-driven actuation and control of physical systems. It's an exciting time because there's so many opportunities to really forward and advance knowledge in this space because of the technology is come down in cost. It's becoming more accessible. It's more pervasive, and we're able to work across disciplines in a much more effective way to solve problems that focus on extending human perception and control of the physical world through digital infrastructure. My team in particular at UC Santa Barbara is really focused in the big picture on climate resilience and designing computer systems that are going to hopefully make that possible and improve or expedite research in this space. But it's really the underlying computer systems that we're creating building blocks for to enable this. And one of the pillars is this digital agriculture pillar that I will talk about today, and that project is called SmartFarm, UCSB SmartFarm. And we're designing the systems that underlie or give developers the ability to design apps and services that execute on farm and in the cloud and anywhere, and to enable the farms of the future that we're all been envisioning and are working really hard to try to obtain. The second pillar that we focus these efforts on is on data-driven conservation, where we work with ecologists and environmental scientists to enhance ecological sustainability by understanding how, in California in particular, how drought has impacted and is changing our environments, and how that impacts animals and plants and all living things. And our primary project that is most known is called Where's the Bear, where we're using animal traps to study wild animals out in the middle of open research reserves to see how their behavior has changed and how their interactions have changed over time with the drought. It's very, very interesting. We also work more recently in technologies and applications that advance climate resilience, both of the computing itself, making it more energy efficient and have a smaller carbon footprint, as well as end-to-end applications in disaster alerts and awareness and prediction. And again, this is all very multidisciplinary. We work on the computer systems, and then we work with experts in these different domains that then when we work together, we're able to design more complex and more advanced solutions to try to make inroads in these areas. So today I'll talk about UCSB SmartFarm. And again, it's motivated by the same I guess you would say, threats or potential that we all see in needing to produce much more food faster as our population increases. We have an event horizon that looks like it's going to be really hard to generate enough food and enough food security across the world. And so we're going to need a lot of automation and a lot of intelligence to enable us to produce this food. In addition, the automation itself can tremendously benefit farmers. It helps them lower costs, increase yields, mitigate the impacts of climate change, reduce their inputs and chemical use, and just in general, they've used these technologies to understand the impact of their decisions, and they're able to make better long-term decisions and track those decisions over time. So it sounds amazing and it has tremendous potential, but the adoption has been really slow. As you know, it's really quite frustrating. It's not widespread. It's not evenly distributed across small and large holders. And so we're constantly trying to understand why that is and design our computer systems either to enable developers to make apps that are more compelling to this population, or to really allow non-technologists to be able to access data and understand their data, and to sort of ask questions about their farms and their operations themselves. How do we bridge that gap from where we are today, where only experts are really using computer systems in terms of programming and development and data analysis, to actually putting this in the hands of those who are making decisions on the ground? And that's the challenge we're all facing, and we all work really hard on, and we need more people to work on. I think one of the challenges, or why it has been a challenge, or why adoption has been slow, is because we've come from a background of cloud computing and data analytics on the computer science side, and it's incredible. The advances have been so swift and so extensive. These technologies in these areas, artificial intelligence and machine learning, and all of the crazy news we hear on the every day now, really shows how pervasive these technologies are and how they've revolutionized our lives. But if you think about them, they've created sort of the killer apps have been recommendation systems, giving us instant access into information, but giving humans this ability to to study and to use human information to give back and create services that provide humans with decision support and recommendation systems. And it's really been the internet of the people, if you think about it. And but if you think about the population of the planet, that's about 8 billion people. If you want to go where we want to go with the Internet of Things, where our technologies are embedded in the world around us, it looks quite different. We can't just take these technologies. What we really want to do is take these technologies from that we've been developing over the last couple of decades and just make them work for these systems, for these other applications that are super important for society. And I just show a few here, and one of them is agriculture. And but just that there's no direct translation. It's actually quite a lift to take the advances of cloud and data analytics and make them work in these Internet of Things. Moving from people to things is a real challenge. The key reason is because the way the Internet of Things uses the cloud and the internet is very different. There's billions of devices, in the 70 billions of devices in use today. And there's about 8 billion people. So the internet and the e-commerce and the entertainment and all the great apps that we have on our phone and in the cloud, they were designed for people, many fewer people. We were consumers of this information. We were bringing information from the cloud to our phones or to our browsers and our laptops. Whereas the Internet of Things is collecting data from the environment and pushing it up to the cloud. And that's a fundamental difference. One, there's way more devices using the internet and the cloud if we're going to use it in this way, and we're using it kind of in the reverse way of what it was designed for. So that actually causes a huge challenge in terms of designing systems and just making this work in a short-term way. This is what on the left is what a data center looks like for the Internet of the people. or cloud and data analytics. There's a handful of these, a few dozen of these warehouse scale computers located across the planet. They are like hospitals. They are super clean. They are super controlled. They are super protected. There's hundreds of thousands of computing devices and storage devices in these warehouses. They're located near power and cooling, so that can be done really efficiently. And this is what the data centers look like. The problem is, this is what my data center looks like. This is a farm in Visalia, California. It produces citrus. It's part of the University of California Agriculture and Natural Resources extension system, and it's not controlled. It's not near power. It's not clean and friendly. It is hot and hostile, and then in the winter it's very cold, and it's very distributed, and it's very heterogeneous. And so all of the technologies that work so well when they're in these kind of centralized locations are now being pushed out to the edge, and it's really challenging to use them straight out of the box. And so we have to rethink how we design computer systems and networking and communications so that we can leverage some of these advances in machine learning and data analytics to solve real problems on farm. The systems research challenges, I always start with this because it's really important for you to see that this isn't just us engineering solutions from what exists. We have to solve new problems from a computer systems perspective. And as soon as we can solve those, then we can really expedite more advances faster. So it's really important that we invest effort and energy into these areas of research so that we can then more broadly integrate with multiple disciplines and larger and more complex solutions. The key difference besides just the sheer number of devices is the heterogeneity of those devices. I work with everything from really tiny microcontrollers with a few kilobytes of memory and storage, and all the way up to supercomputers, high performance computing systems, and everything in between, cloud systems, edge systems. And those systems are very different. They run different software. They run different software stacks. And so it makes it really hard to program an application that's going to run across them. But that's really what we need. And the environments I mentioned are harsh, unmanaged. We don't want an IT staff on farm, God forbid. That's the last thing we want. We want the systems to be automatic and autonomous and manage themselves, but that's still a challenge in computer systems research. The deployments that we see, like I just showed you in the last slide, are extremely error prone and have a multitude of failures that can happen. You can't rely on the communication being there. It's intermittent. You can't rely on the power being there. No electricity sometimes, but other times there it is. And so this intermittent connectivity and power is something that we have to design systems around and not just think of as sort of an afterthought and to make a fix once we've designed a system. We have to think of those as first principles when we're designing systems, because that's very different than what we did in the past. Another thing I wanted to point out that you might find interesting is that these IoT infrastructures, say like a farm that's instrumented or a community of farms that are instrumented or a smart city, these deployments of lots and lots of sensors needs to be reused for lots of applications. So you don't want, just a single application that does irrigation. You want that, and you want the ability to manage frost, and you want the ability to autonomously manage your greenhouses, and the same thing for smart cities. So you want these infrastructures, you want the sensors and the compute that's embedded in the world around us in these cyber physical systems. You want that to be able to be augmented with new devices. We need devices to be able to also leave the system, and we need to be able to use that infrastructure as a digital infrastructure, like we use our freeways, our roads, our cities, for multiple uses. It can't just be for a single use or a single system. And so that also introduces new and very interesting challenges associated with computer systems and how we make use of them and how we share them and how we control privacy and security while we're doing all of that. Next is, because of all this heterogeneity and it's all this distribution and all the complexities of, devices coming and going, connectivity and power coming and going, that makes programming or designing applications for these systems really hard. And only right now, only super experts that are trained in computer science or computer engineering or electrical engineering are able to really make use of these systems well. And so we want to design computer abstractions that hide a lot of this detail so that more and more people from different backgrounds can deploy their apps, can program these systems without getting bogged down in all of the nasty and complex issues that surround heterogeneous distributed deployments. So we work really hard at broadening the developer base of IoT so that we can innovate faster. We need more people involved because these problems are, really hard, and we have a deadline looming out a couple decades from now. So we really need to get started, and we need more people to be participating in it. About a decade ago now, probably over a decade ago now, our first foray into IoT came from us moving from cloud computing and working, even in the commercial sector. It's what my startup company was about. And as we transitioned back to academia, we realized that there was going to be this opportunity in IoT, but there was a real missing piece: the ability to compute out at the edge, not just communicate, not just gather data, not just aggregate and consume data from sensors and then move it to the cloud, to actually do intelligent work out at the edge of the network was just starting to gain momentum and interest in the research community at that back then. And a lot of people were trying to use cell phones. I mean, they're extremely capable devices, but the mobile phones as sort of these intermediate nodes between sensors and the cloud, and there was some advances there. But what we did is we took our experience with cloud computing, and instead of moving all that data from the edge, from these mobile devices to the cloud, we took the cloud and shrunk it down and moved it to the edge, literally to the edge of the network. And the reason why we did this was because the cloud was so successful. It is so successful. People are comfortable with programming in the cloud. And so if we shrunk it down and moved it to the edge, everything that our goal was, everything that worked in the cloud should just automatically work at the edge. And that would start this momentum towards portability, this ability to program anywhere. And so our first, the first contribution of UCSB SmartFarm were these really low-cost data appliances. And these are just small little clusters, actually. They made out of Intel Next units of computation, NUCs. And there's a little cluster of NUCs, and they're extremely resilient. They can be put under high heat or very cold situations, and they still operate pretty well long term. I think we still have some of our early systems are still running, and they run continuously. They've run over a year without any kind of management. So we're getting to the place where they're more resilient, more fault tolerant. But that really comes from the software that we designed within them to allow these systems to make progress when they start to fail. If they're having some disk problems, the disk can repair itself or isolate parts of itself so that the system can keep running. And even processors can fail and the system can keep running. We're not used to that. We're used to just throwing away the device and getting a new one, but it's not going to be the case in the future, and it's not good for our Earth to do so. So we really need to make use of our devices even as they get close and they start to deteriorate. We need them to make they need to be self-healing. They need to be autonomous, and they need to make progress, even if it's a little bit slower or a lot slower. They still need to be able to do their job without going out until it's until they absolutely have to. So we studied all of this, and we hardened these systems for these very hostile environments, dust, farm workers, running over our devices and wires with tractors, everything from like ground squirrels eating the wiring to our sensors. I mean, I'm sure you've all experienced that fun, but that is nothing like the clean laboratories we have on campus. So it's really important that students get out and have experiences like that. The reason why we shrunk down the idea of shrinking down the cloud and moving it to the edge is the interfaces, the way you use the system should feel very familiar. You should be able to direct your browser to a website. That website could be on the internet, or it could be on your farm, and you don't need to know the difference. It behaves exactly the same. And so we would tailor these systems, these interfaces, so that that was possible. You don't even have to be connected to the internet, and you could still use your on-farm edge cloud as if it was Amazon or as if it was Google's cloud. And so that was really important for adoption and uptake, because it was something that was familiar, and we had programmers that were designing applications that worked in the cloud that would also work on the edge without being modified. And that's key. We can't just reinvent and have net new every time we design a new system. And lastly, it was really important that these systems would automatically integrate the all kinds of just disparate sensors. There's so many sensors, there's so many vendors. They want you to have all these different ways of connecting to the internet, but we really wanted to collect that data on farm so that things didn't even have to have an internet or require a service that was going to be paid for on a subscription basis. We really looked at how do we integrate some of these sensors that are coming off the shelf that farmers want to use without requiring them to have, like, say, a cellular connection. I had a farmer once working in the wine industry who woke up one day and he had 14 cellular connections from all the different sensor vendors who had sold him sensors, and it was just untenable, and nothing was coordinated or interoperable, and he couldn't share data, and sometimes he couldn't even get his data back. So it was a real challenge for a while. It's getting better now, I would say, but it was pretty bad in the beginning, and this is happening more and more, so farmers can make localized decisions without that data leaving the farm. And then designing these systems so that they were efficient for machine learning and AI that was emerging at the time and continues to emerge. It's really computationally and it's expensive. And so these edge clouds are small. They are resource constrained by definition to keep the costs low. So we had to figure out how do we make some of these advances useful in the set scenario, and when do they fall short and why. By moving everything to the edge, it also gave us a tool to allow farmers much more fine-grained control over their data and their sharing. And that in the beginning was really important when the sort of the ownership of data was unclear, when these farmers participated with various vendors. Again, it's getting better, but it's really important to give farmers a choice of when they share their data, how they share their data, how they're contributing to the intelligence that these companies are providing. And our edge clouds really provided a nice sort of middle ground to help farmers make the decisions that were right for them. And I don't want you to think there's just the cloud and just the edge cloud. Over time, what has emerged is that what you really want to do is you only want to move data as far as you need to solve a problem. Sure, there's a lot of problems that we want to solve on farm, so that data never needs to leave that farm. But there are some problems, say that maybe if farmers in a same community could share data, we could deal with things like pests and disease that don't abide by farm boundaries. And so we've worked on community co-op clouds where we'll have much more, even more resources available to a community, and they can share their data there, and applications can be written and analyses can be done to understand sort of the broader community. And you can do this at different levels, different regions, at the statewide. And then of course the cloud is still really important, because there's going to be some questions and research that we need to do where we need vast amounts of information across farms, across the United States, across the world, and all of that can actually use the existing cloud infrastructure. But we really need to think of these things individually as we tailor our computer systems and our applications and our solutions going forward, because that's how we're going to reduce energy costs, that's how we're going to reduce monetary costs, and that's how we're going to use these systems most efficiently and effectively. More recently, we've been focused on the software stack of IoT. The first huge problem is that the heterogeneity of sensors, edge systems, cloud systems, everything in between it really impedes innovation because they all have different software stacks. They all have different services, different libraries. They require different programming languages. And all of this is crazy when you're trying to get people who are non-computer scientists to participate in application development and design. So we really need a new software stack that considers how to hide a lot of this heterogeneity, at the same time ensures that the systems are running really efficiently. At the edge and in sensors, you have very few resources. And so you have to be able to operate on these very tiny systems. But you don't want to expose too much of that to the developer or the application designer or the analyst or the researcher who just wants to gather data and perform their analysis. So we've worked on this over the recent past. So this is what we work on today, actually. And we take a two-pronged approach for this. So we first think about how we might redesign the operating system. So if you run, if you have a Mac and you're running OS X, or you have a laptop that runs Windows, Windows and OS X and Linux on supercomputers and the cloud, all of those are operating systems. And these are the fundamental software systems that run on these machines, but they're different. I just named three of them: Linux, Windows, and OS X. For these tiny little microcontrollers, they didn't even have operating systems. And so again, having this diversity of software stacks makes it really hard to program these. You can't just write a program and have it work on any of these. So we want to redesign the operating system for individual devices. And we want it to work on the smallest of devices, and we want it to work on everything all the way up to the cloud. And so what we do is we design it for the smallest, and then we make it possible to expand that to the very large scale systems. So we go from small to tall, is what we say. So that's the operating system. That's going to run, it's a piece of software that's going to run and manage each of these devices, but that's going to manage them in the same way. And it's going to expose those devices with an interface that's the same. So if you write a piece of code and to one of these devices, it'll work on all of these devices. That operating system is called Ambience. And the way we did it, or what is new about it, is that so in order to make it work for the very small, we had to break up the program or the application into very small pieces. But if we reflect on what's been happening in cloud computing, that's already happening. We have microservices. We have what's called functions as a service. The software of the cloud is getting much more fine-grained. And what's nice about this is when you have isolated grains of code, these grains are small, which means they can run on very small resource-constrained devices. But we can also compose these grains into larger and larger services and larger applications. So if we can design an operating system that's tailored to enabling microservices and enable to and designed for enabling composition of microservices, then we have what we want. We have an operating system that runs everywhere, and the smallest piece, the smallest grain, can run on a resource-constrained device like a microcontroller, a sensor, a camera, whatever you have running out in the field. If it needs to communicate or do more things, it can work on the edge, and you can compose a lot of microservices there. But those microservices, once you write them once, you don't have to write them again. They'll just work. We can just deploy them and compose them, and the system's going to give you that ability. It's going to automate that for you. And so that's the design of Ambience. That's our kind of perspective. The other thing that's nice about microservices is they don't do anything. They sit there and they have code, but they just sit there. They don't run all the time. They just wait for an event to occur, and when their event occurs, that's when they execute. And so this event-driven programming model, this execution model, is also excellent for IoT because they're resource constrained. We have batteries everywhere. We don't want to use energy when we don't need to. So like your laptop is running all the time, and it's even when you're not using it or you're doing something else. We don't want that. We want nothing to be running. We want it to be very quiescent and not use energy when it doesn't have to. But when an event occurs, we want the system to be able to wake up and respond and your code to execute. So that's another benefit of microservices that comes to us out of the box. And so we designed this operating system around that. If you're a systems person, there's a lot of underlying computer systems advances that we had to make in order to make this possible. I won't bore you with them if you're more of an applications person, but I wanted you to know that it really did require a redesign of and a rethinking of how we design operating systems. There's not been a lot of operating system work in the last decade because everyone felt that we had already solved all the problems. But it turns out we haven't when we want to work in these new domains. It's relatively new. We're still working on it, and we still continue to improve on it. It's getting much more efficient and robust. And these are just some early numbers I thought I'd share with you, just to get a feel for how this operating system compares to what exists. And one, nothing like this exists. So what we can do is we can take the operating system ambience and we can compare it to operating systems that work on microcontrollers, really, really tiny devices. And then we can compare that same operating system to very, more standard, more general purpose operating systems like Linux. And so we did both comparisons, and we found that at the small end, compared to Mbed, which is a popular operating system for ARM-based microcontrollers, we were surprised actually that we could get ambience to be as small as it is, because Mbed is designed just for those microcontrollers. We designed ambience for everything end to end, but doing it from this microservices model, we're able to get things to be really, really small and have services that are 11 to 88% smaller. And we haven't even started working on our space optimization yet. So we're pretty excited about this. In terms of our memory footprint. And what this means is not that it's small, it's that when you make things small, you can do more with these little devices. And so it makes the devices more capable when you're able to keep things really, really minimized in the operating system. At the other end, it's another kind of unfair comparison, but everybody asks, well, how does it compare to Linux? How much slower is it? And it actually isn't slower. It's less general purpose, right? You have to code to a microservices model, like if you're used to Kubernetes, or if you've heard of Kubernetes, it's the same model as that. Or if you're used to AWS Lambda or Cloud Functions, it's a model like that. It's very similar. If you're familiar, have used those at all, this would be something that you could be familiar with and learn pretty quickly. And so because we slimmed it down just to be about these microservices and are able to kind of get rid of all of the cruft and that is built up in these modern operating, these general purpose operating systems over time, you can make the system much more efficient. And so it's not really an apples to apples comparison, but just to give you a feel, the throughput, the number of requests per second that we are able to handle for these microservice events gets up to almost over 3 times more in terms of throughput, the number of events that we can handle it per second. Okay, so now if we have the operating system, which runs on all the different devices and provides an abstraction from the operating system to like the sensors and to trigger computation in these events, okay, that's great. Each individual device is great, but how these devices interact. Another really hard problem in the IoT space is some of these microcontrollers use some sort of radio communication between them. Sometimes they can actually have Wi-Fi and attach to the edge or the internet. Sometimes they have Ethernet. They have all these different network technologies that just make it really hard to program. You as a developer don't really care what underlying network fabric there is. You just care that communications can occur or can't occur, and you just need to have sort of a messaging layer that allows you to trigger events and get data and move data around and do analysis. And so the next thing we did is we designed a distributed system that linked these ambience devices or other devices. It doesn't have to be ambience, but the distributed system allowed us to hide a lot of the heterogeneity of the networking. It also allowed us to hide where things are stored. Because if you don't have much space, you're going to have to store things on the edge. If you're on the edge, you want to store things locally so it's fast. So what we did is we abstracted away the storage and the networking, so the communication layer, so that and it made it event driven, made it possible to trigger events anywhere. And so now we're able to connect all these different devices together to form a deployment, and then to have that deployment be something that you can write applications on. And you have very simple abstractions. You have a few of the ambience abstractions and a few of the what we call, it's called Spot. We call it C Spot because it's written in C. So Spot, the serverless platform for things. Using the combination of these things, there's a very simple interface, and you just code to that interface, and then wherever CSpot and Ambience runs, or CSpot and Linux runs, your code will just execute without modification. And that moves us toward portability, and then that just expedites innovation, we're hoping. And our early studies of CSpot show that it's much more efficient, about 100 times without much optimization than existing cloud edge solutions. So a lot of the cloud companies are taking their cloud solutions and pushing them out to the edge. But when you design big, it's really hard to get it to work in a small, and you end up having all kinds of, an amalgamation of technologies. So if you try to get AWS Lambda to work at the edge, there's like 7 different technologies you have to get working in order for this to work. It is extremely hard, even for someone who has experience like me. So we're just trying to make that much simpler. And by doing so, by not having all this, switching between systems and software and libraries and services, we're able to make it much more power efficient, because we don't have all this extra baggage that we're bringing down from the cloud. And then what we study, or what my students are studying now, are how do we place your microservices? How do we compose them efficiently so they're super fast? How do we make deployment easier so that you don't have to know what devices are out there? You just say, here's a deployment, and make it work. Here's my application. Going from, here's my deployment, make it work, to what we have today is a big jump. And so there's still a lot of research that needs to be done there, but we're working hard there. We also are very energy aware. So our optimizations for placement aren't just for performance, but we're able to place our microservices near where there's power. So near where they're on a device that maybe has more battery life than another device, because that's doing some sensing, that's being powered off of solar, and its battery is running out because it's been so gray and foggy. And so it's really environment aware, so that we can optimize in different ways. My other students work on how do you make this secure? How do you make it secure in a way that different applications can live together and use the same infrastructure without knowing about each other, or interrupting each other, or stealing from each other? We do that with blockchain-based smart contracts and alternatives to encryption, because a lot of our devices don't have a lot of capabilities. So we really rethink these technologies that are used in modern systems and try to make them work in this more heterogeneous setting. And then lastly, if we can keep our microservices, the individual grains, really small, one question I'm really interested in is, can we just automatically synthesize these, or generate code for these, or generate code for a lot of the stuff that we all program over and over, so that none of us have to program that. Everyone's saying ChatGPT is going to program everything for us. This is a little more challenging, so I think it'll be a while before it catches us. But in the same vein, we don't want people to have to write code if they don't have to. We just have to make sure that the code that's being written is correct and is going to operate efficiently and correct and safely. On the farm side, on the application side, we work with lots of experts with lots of different backgrounds and experiences in order to come together. Our work's really problem driven. A lot of the system design came from seeing what applications we wanted to write first, and then saying, okay, what's the sort of similarity between all these applications? So next, I want to kind of tell you about some of those applications you might find interesting. We do a lot of work with trying to make zone identification for site-specific zone management. So for precision ag, you want to figure out, where there's areas of similarity in your soils, and that changes over time. Especially with all the rain we've had in California, a lot of our soils and our zones have changed quite drastically with the runoff and the impact of water that we haven't had for a while. And so you want to continuously measure, the soil, but you got to do it really, really cost effectively. It has to be super cheap. If you could automate it with a robot, that'd be even better. And so we constantly work on problems associated with how do we make it really cheap to collect information about the soil, like electrical conductivity, but then we have software that makes up for the sort of the limitations of using EC to estimate soil health, and then we're able to produce these decision support systems that farmers can use and watch over time to see how their soils are changing in terms of their variability. The next one that you might find interesting is just microclimate monitoring and estimation. We use it for frost protection in the Central Valley of California. We have a lot of citrus crop, and it's very prone to freezing and frost damage. And so but if you want to combat frost damage, you have to turn on massive fans, which have huge engines. So like big old semi truck engines, use a lot of gas, produce a lot of pollutants. And there's dozens of these on farm. And so if you don't know which one to turn on or when to turn them on or how long to leave them on, our farmers don't. It's a gut feeling. They have experience. They use that experience to decide this. But the fans cost money. It cost them a lot of money. I had one farmer tell me that the use of a fan, his fans and the gas and the manpower for monitoring it was in the tens of thousands of dollars for an evening, and most of the time it didn't hard freeze. And so, it's a real frustrating thing. And if we could automate this, we can reduce the manpower that's required. It's a really terrible job to be out there all night, and also to get this to be much more accurate so that we can turn on just the fans that we need, if at all. Another solution that farmers use is to use water to put up near the trees themselves, and that causes a slight warming, but the water, of course, is really limited in our state. And I talked to another farmer who used water to manage frost, and he did this multiple times during the year. And one frost event, when he used water, he used just as much water as he used for an entire growing season in one night. So if we can get this right, I think we have a lot of opportunity to really reduce the inefficiencies in how we do things now. And lastly, what I'm really excited about, and this is what we kind of focus on more recently, is controlled agriculture environments. We have access to a 4-acre screen house. It is actually a screen. Wind blows through it. You have weather in it, but it does modify that weather. And so the decisions you make about farming within these screens changes. And we're using the screens to exclude bugs, pests that are actually bringing in disease. And citrus, we're worried about citrus screening, but we're really trying to understand how we can bring down the cost of using greenhouses for large scale farming situations. We have the psyllid that carries the disease that causes citrus greening is in Southern California, and it's moving to Northern California. It hasn't made it there yet. And this is the first greenhouse that we have as an experimental platform, but we're all thinking that it's going to make its way, and that's going to really change the citrus industry. And so we're working with experts to try to mitigate some of that and see what the opportunities are for using screen-like technology to protect some of our crops. It's used in all kinds of different ways, though. It's not just for citrus. It's not just to protect from plants. We've seen screens used across the world for to prevent sun damage, also weather damage. There's extreme weather events that are actually causing quite a lot of harm to different farms, and there's people looking into it for that reason. But once you have a structure like this, you can do all kinds of interesting things. Like you can harvest energy from the structure itself off the cable lines that are holding it. You can you need to change how you spray, because how the sort of the temperature gradients inside the screen are different. The way sprays move in the air is different, and we have to model that differently and make different decisions. So we study all of this. We're putting together a system that couples complex fluid dynamics, so advanced physical simulation with data-driven computation, and seeing if we can do sort of what-if simulation. They call it digital twins now, but people have been doing it for a while. But to look at on-farm and sort of off-farm virtual and real settings, and how we can explore these settings to really forward and advance research. So if you're interested in any of these topics, I just want to throw them out there because I would love more collaborators. We also have a farm robot that is autonomous and can do a lot of our sensing. We have a sensing platform that we work on with this and do a lot of computation on this device itself that you see in the bottom right of your screen. And then lastly, we do a lot of image processing. Images contain tons of information, and we look at what we can infer from those images that we could use instead of putting sensors out in the field. So for example, if you could take pictures from a camera that's really cheap and maybe is far away, you don't have to put sensors out in the field, and so you save all kinds of costs that way. But also we look at how we can power these devices and things like that. So I'd be happy to talk to you more about those things if you're interested. I just want to kind of give you a feel for the applications that we focus on. All of our systems are designed in the lab and tested and developed in the lab, but really we push our students to get them out there into the field as soon as possible. The earlier we put these systems out there, the more understanding we have of how challenging this is, but what novel advances are needed to make this possible. And this really is all about collaboration. I couldn't do this without real test beds. We have an edible campus program, a student farm on campus at UCSB that feeds food insecure students, and students manage the farm itself, and we're able to use sensors and help guide them with data-driven information to help them make their decisions about what they're doing to the farm on campus, and they get really excited because they've never really had access to digital or education on digital intelligence. So there's a great way to give back, but also to learn from and have real users kind of give us information and help with the systems designs that we're coming up with. And of course, we work with real farmers and farmers that are growing all kinds of different crops. And that top right there, California is just so diverse. It's so different than all the other states. There's a couple of states that are similar, but not this diverse in terms of what we produce. And so we can really explore different types of crops. In my area in Santa Barbara, we have lots of strawberries. I said we worked on citrus. We've worked on grapes for wine and table. We have access to lots of tree nuts, so almonds and pistachios. And all of these require lots of different solutions, but we're hoping with a sort of a standardized software system, we can allow developers and designers and researchers like you to tailor your solutions to these different crops, and really we can all make progress together faster if we're able to do so. So in kind of summary, I think we're really envisioning and rethinking how computer science and computer engineering research is done. I think that we need to do so in order to expedite innovation and get it out there for some of these harder problems that are facing society. They have to be problem driven by real problems that society faces, not that we make up. It's got to be empirical. You got to be able to measure them. They have to be real test beds, real farmer collaboration. And this is why I've really enjoyed and been proud to just be able to watch IoT4Ag. I mean, because this is really what's behind it. It's multidisciplinary research. You guys call it convergent, but it's really about coming together to solve these hard problems. And I think this is really the only way. But it's also really rewarding to have societal and regional impact and also makes our technologies and advances tech transfer ready to hand to growers to get them to try it, if not use it. And if we can get closer to that, we're hoping to kind of eat into the adoption challenges that are getting better, but still need to have more inroads made. And lastly, we really want to attract many more students to this area. I think that a lot of our young people feel really strongly about impacting society, and this is a great way to do it, either with technology or science, or even lots of humanities advances that we need to understand the population and the society that we're introducing this technology into. So coming together and engaging a diverse set of students is also really important. So with that, I will stop. I just want to say I can't do any of this without an amazing team. My co-lead, Professor Rich Wolski at UC Santa Barbara, all my amazing students, and there's been a few that have been added. I just didn't get their pictures up in time. Sorry to them, but they're amazing and they do most of the legwork. I also have tons of collaborators that really inform how we think about computer science and computing, and really help us understand the ag problems and solutions that are needed so that we can try to come together to bridge that gap. And I know that IoT4Ag does a lot of the same things. I think it's important, and it's not a competition. It's that we just need more and more people. If we could get everyone working on this, I think we'd all be better off. So if you're interested in working or talking more, or if you have questions, I'd be happy to answer them either here or feel free to contact me. We can talk offline and afterwards. So with that, thank you so much for listening, and thank you so much for inviting me to give you a seminar.
Thank you very much for this inspiring talk. We have time for some questions. You can either type those questions in the chat, and then we're going to read them, or you can raise your hand, and I think Holly can enable your mic. Let's go. We already have 3 questions in the chat. So the first one is the following: what kind of essential building blocks should be built for edge clouds on farm, and how complex should these building blocks be?
So from a systems perspective, there's a couple challenges. So we want lots and lots of abstraction to make it super easy to start building applications. At the same time, those layers of abstraction must be permeable enough for, if you want to understand what's happening, if you want to make it more efficient or optimize, we got to give the developers and the applications designers the ability to do so. And so that's our challenge, is that we can't make it completely abstract and just solve the problem and automate everything. At the same time, we can't reveal too much too early. And so that is really the challenge we work on. And so I think in terms of the building blocks, we've started them. You want to have you want a bunch of services is really what you want. Your abstraction should be a bunch of services. You need to be able to store data, get data from a sensor. You need to be able to pull data and combine data into aggregates. You need to be able to perform analyses that you're comfortable with. All those can be encapsulated in services that you don't have to write. You can just say, hey, give me my data. It's this data that I want. From this analysis, produce my result and put it here. And then you can go and get it. That's what we envision. We're building the software stack to make that possible. And we still are designing the services to make it easy. It's not easy yet today.
Many thanks. And the next one, actually, Holly will enable the speaker to ask the question.
Hi, Dr. Krintz. I really appreciated your presentation. I know you had talked quite a bit about the microservices, the operating system. Do you think data standard is also one area we need to focus on? Because as you said, with heterogeneity of all these different sensors, all the different observation measurement that comes through, having an ability to have a common data standard that allows us to have better interoperability could also be one of the toolkits we need to have as we build this?
I do. I think you're exactly right. I worked on this a few years ago, and when I found I was really frustrated because it's really hard well, it'd be hard for us just sitting here to agree on things because we all feel strongly about how things work. So as we expand that out and we got industry involved and lots of academia and lots of big thinkers, it was really hard to come to an agreement on what a standard would be. So I think my feeling is that there'll be a small subset, and we kind of have to put a bunch out there and see what takes. So, you know, a lot of the cloud technologies, the winners came from just people who found these services and used them. And we kind of need to have let that happen organically. What we've done is we have, I don't talk about it today, but we have a system called Depot. It's a data sharing platform, and you just put your data in there, and it can be in any format, and it can be from any source. And then different people can use it, and it's transformed into the sort of the model or the format that the user wants. So we've kind of taken the Switzerland approach, where we'll let you have any sort of format or sort of even a customized one, but I don't think that's the end game. I think that's still way too complicated. It's way too hard, and I'd love to talk to you more and hear about where you think the best place to invest time and energy is, because I think that's probably what our next steps need to be.
Yeah, and then exactly right. I mean, there exist a lot of data standards even within the space of ISO. There's ISO 19156, 115, and so forth, but none of those are geared towards agricultural observations and measurements, if you will, if you look at it in the small scope. So yeah, I do believe there is room and need for collaboration to further work on it. As you said, you have an ingester that can do it, but it still doesn't solve the problem of making the data standards sort of in some universal format, right?
That's right. That's right. Exactly. And I think we need to not only sort of start designing that format and, leveraging, sort of what you're saying there and your ideas. At the same time, we got to get it out to the community. We got to get it out in farmers' hands, farm consultants' hands, agriculture specialists' hands. And I think we have to design it with them. Because we got to get uptake, and if we can show that people are using it, we have a better chance at a standard actually coming into being. But great question. Yeah, good point.
Hi, Chandra. I hope you can hear me. This is Sherry Kagan.
I can.
It's a little intimidating on the webinar format, but I just wanted to thank you. That was really great. And I wanted to ask you a question. You talked about screenhouses, which I had never heard about, and I think are really interesting conceptually. Are they mostly used for pests? Or is there any other functionality in those screenhouses to regulate light? And what I mean by that is either the wavelength that comes through potentially to affect the growth of the crops, or an intensity to not overexpose, for example, or even to regulate temperature so that we control crop stress.
Yeah, so I think it's there. That's relatively new. The reason why, so it's a mesh. Yes, it's a mesh. People have looked at it in a small scale for sun damage to reduce kind of exposure. I've seen it where they're trying to reduce irrigation, the need for water, because it's much more humid under these meshes. And interesting, because that's interesting. But it's not, I wouldn't say in widespread use, primarily because it's pretty costly. And so I think that's been the impediment, but I think it's tremendous potential for this. It's just, too costly right now.
Thanks, I really appreciate that. I was just thinking about whether, I'm not sure it would affect the cost phenomenon, but if we think about some of the large area fabrication techniques that we have been working on in the center, there are ways to think about how to control both light and temperature. And so I was just thinking about it as you described it. Thanks very much.
Yeah, and I just want to follow up right there real quick is when you control light and temperature, it actually then has an indirect effect, of course, on how sprays impact the crop and how they hold on. I mean, I'm not an expert in this area, but I've been told that when there is more humidity, there's some sprays will actually adhere to the leaves better. I mean, there's all these different things that change that might actually in the long run, end to end, reduce costs because we have to do less with by investing in something like this. So yeah, I think you're and like you said, the sort of fabrication that you guys are doing with yeah, I think it's really exciting and there's probably a lot of potential there. So thank you for the question.
Yeah, thank you.
Okay, we're almost at the hour, so maybe I ask the following. There are a couple of questions from UC Merced folks who will meet with Chandra right after, so maybe we can defer those for the individual meeting, and then we take the last one. Well, there was a comment. Yeah, I don't know if Ed wants to bring it up live, or maybe we can close now, but it's 11. Yeah, Ed, go ahead.
Oh, no, I think you're dead on target with the need for some of the standards to make this all happen. So I just wanted to say there is some work in progress through both Ag Gateway, and then that ISO has a SmartFarm strategic committee looking at that question as well. So that's all.
Super. Thank you so much. Write it down.
All right, thanks everyone for attending. Now we switch to individual meetings with small groups. You should have received links. I don't know if Ollie has some last minute announcement. Otherwise, we thank the speaker for the great talk.
Thank you.
Thanks so much, Chandra.
Thanks all. Thank you.
Bye, everyone.
Bye.